Alright folks, here's what's going on. We're going to be doing chemistry today, and today we are finally starting up on chapter 2. It's only 4 weeks into the class, and we have made it to chapter 2, folks. Alright, now, I don't know if I'm going too fast. I kind of feel like I'm going too slow, but that's fine. I'm going to go at the pace that you folks feel comfortable with, and I feel like I'm going at a good pace. I feel like if I go any faster, it would make your brains hurt, and your brains will turn to jello and whatnot. This week doesn't have any due dates for chemistry. Does that mean I don't have anything to do? Oh no, my friend. That just means Mr. Dalday hasn't finished assigning them. I finished actually making all the homework, I just didn't assign it yet. I will assign it, don't worry. You can have a lot of chapter 2 stuff due today, I think. Or not it can be chapter 2 stuff. Anyway, I'll make it so that way you'll have the homework assigned. Give me till tomorrow to be able to finish that, alright? Alright, so here's the thing. Chemistry, to start off chemistry, here's what we need to start talking about. We need to start with our ABCs. All right, we need to start kind of telling you folks about the different names to use, the different things that we use. Before we even start doing real full-on chemistry, we need to get everyone caught up with the nomenclature. Has anyone ever heard of that word? What does it mean, nomenclature?
Technical terms.
It's basically, I don't know, I kind of think of it as the word for the naming convention. You know what I mean? Like there's a certain rules that you follow for naming things, and there's also a certain, so in chemistry there's going to be a certain way of we name things. But I mean, like I guess a good way to think of nomenclature is, like my name is Anastasio Tui Dalday III. That's my name, right? And then my dad's name is Anastasio Kaluuya Dalday the Jr. And then my grandfather's name is Anastasio Lagarat Dalday Sr. And my son is actually Anastasio Dalday IV. There's a naming convention. What we did to get all of our names is, obviously the first name is Anastasio, the last name is Dalday, right? But what my family chose to do was we said, all right, we're going to take the mom's maiden name and take that and make that the kid's middle name. So my mom's maiden name is actually Tui. My dad's mother's maiden name, my grandmother's maiden name is Kaluuya, which is my dad's middle name. Does that make sense? So there's this like naming rules that we practice in the Dalday family, at least for 4 generations. Although I broke the rules because my son's middle name is Griffin. And I just made it up because I thought that was a cool name. So, yeah, Mr. Dalday was like, you know what? I don't want to do that convention. So I messed it up for everybody. But hey, sue me. Griffin's way cooler than my wife. Actually, I can't say that. My wife's last name is pretty cool. It's Adams. It's a pretty standard name. So no, it's not. It's like Griffin, like the magical creature, not like Griffon, like Griffin. Actually, I'm sure that's how you spell Griffin, the magical creature. It might even be spelled with a PH. That's neither here nor there. What we need to do is we need to be able to kind of come up with a specific language for us to start talking about chemistry. And you folks are thinking, hey, wait a second, haven't we covered that in chapter 1? And my answer is no. Chapter 1 is actually the specific language we apply to all sciences. It's called math. And that's what we did in chapter 1. So chapter 2 is starting to get you folks up to date with like the ideas of atoms and molecules and ions and nomenclature. Chapter 3 and 4 and 5, that's when we're actually going to put the pedal to the metal and do some actual full-on chemistry. Are we cool? Which is not to discourage you. I mean, this stuff is kind of tough. All right.
So less numbers?
So less numbers for this chapter? Yes. I believe there's a lot less numbers. Does that make you happy or sad? But don't quote me on that. I think that there's less numbers. I'll have to check again. All right. So, what I like looking at, what I think is really interesting is the history of chemistry. All right. And also, just to kind of give you a heads up, I'm going to try to finish this lecture really quickly, and then somebody requested that I go over chapter 1 stuff. Just as extra help. So I'm gonna do that. I'm gonna do this lecture kind of quick, and then introduce you to chapter 2, and then on Wednesday we'll cover chapter 2 for hour and a half or whatever, however long we have for that day. And that particular day I'll probably take up the whole time. All right, so the Greeks were kind of the first people to come up with this idea of atoms, and what they kind of asked themselves is they said, are things discrete or continuous? And what that means is, if I have something, can I cut it down, like, I don't know, let's say a pencil, the pencil you're holding in your hand. Could I cut that in half? Yes, of course. Can I cut that in half? Can I cut that half in half?
Yeah.
Sure. Can I cut that half in half?
Yeah.
All right. Can I keep on going?
Yeah.
Forever?
Yeah.
No.
Well, see, that's what the Greeks asked themselves. And this is really interesting because this was like more than 2,000 years ago. So, I mean, these guys are sitting around and they don't have microscopes, they don't got computers, they don't have electron microscopes, they don't even know what an electron is. And they're asking themselves this question: can I cut something in half? Can I cut that in half? Can I cut that in smaller pieces? And then they said, I wonder if the world exists so that you can keep cutting things down smaller and smaller and smaller and smaller and smaller forever, or if at some point your knife doesn't work anymore, it cannot cut something down. And obviously you folks now, 2,000 years later, know the answer. And the answer is what? No. You cannot keep cutting things down. You're basically going to get down to where you have a single atom. Can you cut that in half? Well, now we can, but before we couldn't. But you're going to have things that make up the atom, like quarks and protons, neutrons, electrons. Can you cut those in half? You know what I mean? Well, I guess technically now you have quarks, but can you cut the quarks in half? No, not yet.
We don't know yet.
Us physicists haven't come up with a way. So at some point it stops. This game stops. Got it? And then, in the history of chemistry, for 2,000 years, they had this kind of pseudo-chemistry that they called alchemy. And alchemy was like, that's where a lot of people tried to get rich by turning, like, iron into gold. You know what I mean? Has anyone ever watched the show Full Metal Alchemist?
No, but I've read The Alchemist, which is a really good book.
Oh, you've read The Alchemist?
Yeah.
In fact, I actually just gave... Whoa.
What the heck?
What happened? Did you guys...
Yeah, I lost the display.
Huh, okay. Give me a second, folks. I think my display got messed up. Big blue button. Sorry. Give me a second. All right. Well, don't worry. I've actually never watched Full Metal Alchemist, but Alchemist is kind of like... I guess I never watched it, and I never let my kids watch it, because alchemy was kind of associated with magic and witchcraft. And I'm not really into letting my kids watch witchcraft and that kind of stuff. But essentially, when my wife and I decided, let's not have the kids watch the Full Metal Alchemist or whatever, this cartoon show, because we thought that it was about witchcraft. Well, that's what alchemy kind of was. It was like, it wasn't really a science, it was kind of a pseudoscience. So a lot of people who were really into alchemy for those 2,000 years were like considered more magicians than scientists.
Isaac Newton was an alchemist.
Which is not to say that the alchemists didn't actually do science, or that they weren't scientists. It's just the science of alchemy itself has been disproven. But, yes, you're right. Isaac Newton did exist within that 2,000 years that alchemy was popular. And so, therefore, he probably was an alchemist. Actually, he was an alchemist. Although I haven't read a whole lot of papers of his on his alchemy in interest. All right, let me know when you guys can see my computer screen. Is anything showing? There's two Mr. Daldays, because one of those Mr. Daldays is sharing his computer screen, and the other Mr. Dalday is You kind of see it. What do you kind of see? I don't see anything. I don't see anything. Well, that's a pain. All right, I'll tell you what. We're switching modes here. All right. Oh, that class is cut short. All right, give me a second. I'm going to log out on everything and log back in. I got an idea. Okay, we're going in here. Conferences. Join. Let's run class through this way. Whew. What are you chatting about?
I'm just texting my mom to see if she could.
That's always his excuse.
Sorry, taken.
Yeah. Yeah, sorry. That device or that excuse is already gone. All right.
I actually was though. It's not an excuse.
No, I know.
Try again.
Yeah. All right. Okay, let's go back to our full screen. Share the thing, please. Audio check 1 2. Check 1 2. Can you hear me? Awesome. All right.
Can you hear me?
That was Tejas, by the way. Let me know when you can see my computer screen. Oh, wait, what is this? All right, here we go. All right. You guys got the computer screen? All right, cool. Let's do this. Present. So, we talked about alchemy and how it was basically magic science. It was like Magic the Gathering meets science. Do you guys play Magic the Gathering? Or is that like too old for you? What do you guys play, like Yu-Gi-Oh now, yeah? You guys don't play, or you guys just not, that's not cool enough for you?
That's not cool enough for me.
Excuse me, sorry. All right, so check this out.
No,
The
I
first-
just don't play card games.
The first chemist was, his name was, we consider the first chemist to be named Robert Boyle. And what he did was he actually performed experiments where you didn't just kind of sit around and think about things, but you actually measured things. And it was really important that he came about. So Boyle did a lot of work with gases and how chemicals behave in different gases, and he talked about pressure. And there's an actual chemistry law that we're going to be learning later on called Boyle's Law, which basically has to do with gases.
Ironic since it's Boyle's Law.
Yeah, you know. Isn't that cool? All right. Lavoisier. All right. These guys are going to have really French names, and I'm going to screw them up. Does anyone speak French here?
Lavoisier.
Are you're French kind of?
Yeah, my mom speaks French.
Lavoisier.
Whoa.
All right.
Lavoisier.
Lavoisier. All right. Lavoisier, he was a pretty cool dude. He kind of came up with this idea that mass is a constant. Oh wait, I didn't want to do that. I wanted to do this. He kind of came up with this idea that mass is a constant. He said mass, the conservation of mass. Mass can neither be created nor destroyed.
Oh, shoot, Stan.
All it can do is change from one type of thing to another. And that was Lavoisier's contribution to the world. sucks to be him because even though this dude was awesome, he came up with these things. He actually collected taxes, and he existed around the time when they had the French Revolution. And the French Revolution said, "You collect taxes, you must work for the king." And so they associated him with the government, and they cut off his head with a guillotine in public, Times Square or whatever, in the middle of the thing.
Did you know the guillotine wasn't banned until 1984?
I know, isn't that crazy? All right. Did you know that people still stone people to death?
In France.
Yeah, I know. That's crazy. Anyway, all right. So Lavoisier
We do not like you Americans.
was really cool, but then he got hit by Vive la France, all right, and which is a big problem for him because he no longer has a head. I don't make a joke out of that. That's not really that funny, but
Yeah, it is.
I don't know why you're laughing. That's terrible. All right. There's this dude named Proust who came up with this idea after Lavoisier. He was one of Lavoisier's followers or students, and he kind of came up with this idea of definite proportions, which is a really interesting thing. Like, here's something that they came up with. This guy named Dalton, which is expanded on Proust's idea of definite proportions, and he came up with this idea of the law of multiple proportions. So here's what happens. All right, think about and this is where it gets really interesting to me. Is let's pretend that they're experimenting on this very common substance called water. Okay, and everyone knows the equation for water, right? What is it?
H2O.
H2O. Okay, good. All right, but pretend you're back in their day and you didn't know the experiment on water, okay? And so what you did was you said, I have pure hydrogen over here and I have pure oxygen over here. And if I give the hydrogen 1 gram of oxygen to react with, how many grams of hydrogen is it going to use up to make this water, okay? And so what they did was they said, they did experiments on this, and they found, exactly 8 grams of water, or 8 grams of hydrogen, reacts with 1 gram of oxygen to create this thing, okay? And what I think was really interesting is these proportions were always the same. So the reason why this is kind of crazy is because when you take 1 gram of oxygen or whatever, and you react it, you take like the ratio, they always come out to be a whole number. And I think that's crazy. Because you figure if you take 2 numbers and you divide them, you wouldn't get exactly a whole number. Does that make sense to you?
You might get hydroniums.
Well, I mean, you might get different things, but you wouldn't get like a straight up whole number every time.
Yeah.
And so they were noticing, hey, there's straight up whole numbers every time. And so they were trying to figure out, like, what's the deal with that? You know what I mean? And so then they realized, hey, when I break it down at the molecular level, this is a good evidence to say that I can't cut things down smaller and smaller forever and ever. Things have to have, like, definite molecules because they divide into whole numbers. Does that make sense?
Yes.
If I could cut it down, then I could have had a fraction of that molecule. You know what I mean? To deal with. And then things wouldn't divide into whole numbers. So since things can't cut down, and there are actually, like, you can imagine, like, little these little the oxygen molecules and the little hydrogen molecules. If I take those ratios, that would be their exact numbers, their exact ratios. There's exactly 2 hydrogens to 1 oxygen. Got it? I hate to say it, but Dalton actually kind of came up with this concept, and it was genius when he came up with it, but he got it wrong. And
Stupid.
well, what happened was he said that he said that the oxygen is 8 times bigger than hydrogen.
Mm.
Because what he said is, oh, hey, it's only 1 gram of oxygen, 8 grams of hydrogen, then the equation must be OH, right? Or HO or something like that. 1 hydrogen, 1 oxygen.
Oh.
And so hydrogen is 8 times bigger than oxygen. Or, oxygen is 8 times bigger than hydrogen. Does that make sense to you? Yes? No? Yeah?
Isn't that the point? It's not supposed to make sense.
No. Actually, it's what he did was he didn't know that the equation was H2O. He thought it was HO. And the reason being is his concept is he said, well, it's a law of nature, so it must follow the simplest form.
You burn me.
You know what I mean? Instead of having 2 H's and an O, he just theorized, the equation must be OH. So what he did was he came up with this idea that oxygen is 8 times bigger than hydrogen. And he kind of took all of these elements and made a table out of them. And that table happened to be kind of periodic. So we ended up calling it the... What?
Yeah.
The periodic table.
Yeah, you.
There we go. All right. But the problem is he didn't know the exact equations, so he kind of got them wrong. He got a little bit wrong, but he was onto something really awesome.
Non-periodic table?
Yeah.
Right.
Dalton's atomic theory is he theorized from this experiment that each of these elements were made up of tiny particles that he called atoms. The atoms of a given element are identical. For example, if I take oxygen and I have 1 oxygen atom, it looks exactly like another oxygen atom that I have in another spot. They are identical. Got it? Chemical compounds form when different atoms, or when atoms of different elements combine together. So, for example, H2O. It's 2 different kinds of elements, the atoms of 2 different elements pulling together. In this particular case, it's 2 H's and 1 O, and it forms a chemical compound. Cool? And most of what we see in the world is not just straight up pure substance. Most of the things we see in the world... Did you just try to fall asleep?
No.
It looked like you just nodded off.
Yeah.
You were like...
Yeah. That's right. I do that all the time in my math class, but I'm just saying. All right. Different elements of the periodic table, most of what we see aren't pure, so they kind of combine into different materials. Let's see.
That was horrible.
So when a chemical reaction occurs, what happens is the atoms reorganize and combine in different ways, but the atoms themselves don't change. I can change one chemical compound into another chemical compound, yes? Correct?
Yeah.
Yes, I can. But the actual atoms themselves didn't change.
Just the composition.
Just the way it's composed.
Organized.
I mean, I
Arranged.
could like take off electrons and take off protons and whatnot, and that could change things around.
You're God.
But anyway. All right. Concept checked. Oh, look. This one asks for the answer and gives you the answer at the same time. Which of the following statements regarding Dalton's atomic theory is still believed today? Elements are made of tiny particles. True. All atoms of a given element are identical. Actually, that's false. A given compound always has the same relative numbers and types of atoms.
Why are you giving us false information?
Well, what I'm doing is I'm showing you what they thought back then, so that way we can kind of say, okay, this is how chemistry and later experiments has changed this concept. By the way, you figured that would be true. All elements of a given all atoms of a given element are identical. You thought that would be true, right? I actually convinced you that it was true. I said, if I have one oxygen over here, it's exactly the same as that oxygen over there. Right?
Yeah.
But why is it wrong?
Because you don't know.
Okay, well, I'll tell you why. And maybe you folks have had this a little bit in like general science. I think that maybe 7th grade science, 8th grade science covers this. Atoms are made of what? And we're going to go into this later in great detail, but At your middle school knowledge of science, what is it? Protons,
And neutrons.
neutrons,
Electrons.
electrons.
Quarks.
Good.
And quasars.
No, quarks are actually what
I'm kidding.
protons and neutrons and electrons are made of, but I'm just saying
So then,
atoms are made
by
of.
extension, that of it.
Yes, but you can't say and quarks. All right. Essentially, protons, neutrons, electrons, right? Protons are what? They negative or positive? Or
Positive.
positive. Electrons are
Negative.
negative.
We gotta be so negative.
Neutrons are
Neutral.
neutral. Got it.
Obviously.
Could I have an oxygen atom that has extra neutrons?
Yeah.
Sure. It would just be a heavier version of oxygen. So technically, all atoms are not identical.
That sucks.
Could I have an oxygen atom that has extra electrons?
No.
Yeah.
Yes.
Yeah, you can. In that case, it would be a charged version of oxygen. That oxygen would have an extra charge on it.
I see.
Because there's like one too many protons, or one too many electrons, or one too less electrons.
Roger.
Does that make sense? But it's still oxygen. It's just a different look, or a different charge on it. Yeah. So that's why atoms that have different or atoms of the same element don't exactly look identical. And then the other idea that he came up with is he said atoms are indestructible, but that's not true either, because we know that atoms can be broken up into smaller pieces, which we've already named: protons, neutrons, and electrons. At this point, he didn't know that, though. I think that what's really interesting is this guy was able to do these experiments by just weighing things. I mean, imagine doing that. Imagine trying to figure out the fundamental laws of how the world works with things you cannot see with a scale. He didn't even have a stopwatch or anything, or an electronic balance. He weighed stuff. That's cool.
That's tedious.
All right, wait 1 second. I gotta tell my wife I can't. Yeah. I gotta just. There. All right.
Uh-oh. Uh-oh.
Well, if she calls again, then I definitely gotta answer, because that means it's an emergency. All right. I'm gonna go into this guy, but before I do that, actually, I'm gonna stop now, because what I want to do is I told you I would put you guys on pause. I'd finish off the rest of this lecture later on, and I'll come back to this. But before I do that, can I ask the French guy in the class, pronounce this? This would be you, Tejas.
You suck.
Oh, there's my wife calling again. 1 second.
It's an
Hello? Hey, I'm actually in class right now. Could I call you back, or is it an emergency?
His name's Gay Lusak.
Okay. What do you want to say? Where are they?
His name is Gay Lusak.
Okay, I think that they are in the workbook or in the teacher's
Oh,
manual.
that's gotta suck.
That's what I saw. They were like day 4, I think. All right. All right, I'll talk to you, kid. Love you, bye.
Oh my god, I don't know why that's so funny.
What? Guy Lusak?
Gay Lusak.
That's just how you that's how you spell it. It's not how you pronounce it.
Well, Lusak is, yeah.
What?
It's Lusak.
Gay.
Lusak.
That's, his name is Guy, right?
He's a Lusak in his name.
What does Lusak mean?
I can't remember. I don't know.
Anyway, I think it's Guy Lusak.
I'm pretty sure it's gay.
Right. If I were more tired, I'd probably pronounce it differently. But it's Guy Lusak. All right. Anyway, French dude. Okay. So chapter 2 stuff.
This
Lecturing
Lusak.
is done. Anyone have any questions about chapter 1 stuff that they would like for me to cover? Emily?
They're writing.
I got one person saying, Converting. Okay. Unit conversions. I'll tell you what. I am going to open up the floodgates so you folks can...
Care.
Yeah, of course you can move on to chapter 2. In fact... Yeah. Yeah, but you're not doing the French version.
Yeah, I am.
Oh.
English to French.
Okay, the dude's name was Guy
Guy.
Lussac.
Get the sack. His name is Mr. Gale.
Wow.
I don't know why. I'm really punchy. I'm tired. That's why.
Yeah.
Yeah.
Your maturity level's like right over here. All right. Anyway. From 1 unit. Yeah. No, I know, Bradley. But here's my question: is which problem specifically do you want me to cover, Emily? Do you have like a specific problem, or you want me to just be like, I don't know nothing. I wanted to cover everything. Because if that's the case, I'd refer you back to the videos and say you should watch the archives. And actually, I need to make that as a kind of a general rule. People want to come in and get extra tutoring from me, and I'm totally fine with that. If you want to come and get tutoring, though, I want you to at least watch the classes that you missed. That's only fair to me, because that means I don't have to re-lecture all over on that. But if you want me to do, like, all right, here we go. Okay, you're going from cube units. Yes, that's a good problem. Here's the problem, though, is I can't, my computer, the one that I can write on isn't working, so I got to figure out a way to kind of show you how to do this. All right, let's do this. Okay, update, new tab, whatever. All right, let's try this. LaTeX equation editor. So let's do this. All right. Let's say we have a box that is 5 centimeters.
Gay-Lussac.
Yeah, you're right. It was Gay-Lussac. All right. 5 centimeters by, I don't know, 2 centimeters
Sucks.
by 10 centimeters. Got it? So what you want to do is you want to convert this to inches cubed. You want to convert this from centimeters cubed to inches cubed. All right? So one way to do that is what you say is, all right, well, what is 5 times 2 times 10? It's like 100, right?
Yep.
It's exactly
100.
Like 5 times.
So what I'm dealing with is 100 cubic centimeters.
100. Hold on.
Uh,
Can you give me the volume?
So I'm dealing with 100 cubic centimeters. Cool? But you want to convert that into a inches, right? So what I'm going to do, and by the way, keep an eye on this right here. This stuff down here. So what I'm going to do is I'm going to multiply this by some fraction. I'm going to use it to help me convert the centimeters to inches and whatever. Do you remember how many centimeters are in an inch?
Enough to make an inch.
2.54 exactly centimeters. Are we cool with that? But you see, the problem is I don't just divide 100 by 2.54 and I'm done. The problem is this is converting an inch, a linear inch, to a centimeters, and I need to convert centimeters cubed. So I don't need just one of these. I actually need 3 of them, because I need a total of 3 centimeters on the bottom to cancel out with those 3 centimeters on the top. Does that make sense to you?
Yes.
But the thing is, well, not but the thing is, but I mean, one way we write that is we just put a cube down in front. So what you want to do, Bradley, is you want to divide 100 divided by 2.54 cubed, and that will give you the cubic inches. You got it? All right. One way that I told you to do it, and I said, you can either do it this way, or what you could have done is you could have converted each of these 5 centimeters, 2 centimeters, and 10 centimeters into inches first, and then multiply them all together and get the volume. Mathematically, you're actually doing the same thing. Do you know why? Do you know how? All right. In order to get the volume, I multiplied 5 centimeters times 2 centimeters times 10 centimeters, right? In order to convert the 5 centimeters, I would have had to convert the centimeters to inches, right? So I did that for the 5 centimeters. I should have also done that for the 2 centimeters and the 3 centimeters.
You should have what? You should have.
Well, what I said is there's 2 ways you can do it. You can divide 100 by 2.54 cubed, or what you could have done is before you multiplied 5 times 2 times 10 together, you could have converted that to an inches, and convert that to an inches, and convert this to inches. Does that make sense? And then multiply them all together. But look, mathematically, I'm doing the same thing, because I think that there's the associative rule, or no, it's the commutative rule. Do you guys remember that in multiplication? I can multiply in any order I want. So I can kind of multiply these guys, all 3 together first, and that's the 2.54 cubed, and then I've got the 100 because that's the 5 times 2 times 10. I could just, multiply it in any order I want. So mathematically, I'd be doing the same thing. Yeah. Exactly, Bradley. What you would do is you would divide the 5 by 2.54, and then divide the 2 by 2.54, and then divide the 3 by 2.54, and then multiply all of them together. Or you could multiply them all together and then divide by 2.54 3 times. All right. Anybody else have any questions about conversions? I thought you had a whole section you wanted me to cover.
No, I just wanted you to go just one problem.
Oh, you want me to do a problem?
Yeah.
Like the kind problem addition.
All right.
From our homework.
All right. You want me to do the star problem was hard. Which one's the star problem?
In additional problems.
Oh, there's in additional problems. There's a star problem.
I don't know.
Well, hey, the star means it's going to be the harder one. So don't feel bad if you don't get it. Let's do it then. Additional problems. The star.
I don't see a star.
Which one are you talking about? Oh, the one that I talked about, a star. That would be... Thanksgiving turkey. No, it's not an additional problem. That's in unit conversion. Hey, by the way, was there a mistake that I made in additional problems? All right, no one said anything, so I'm going to say no. No, Miss Dalda, you were perfect.
You're a perfect human being.
All right, where's my thing on conversions? Where's that homework assignment? What was it called? Oh, was it density? All right, let's do it.
Get a new puppy.
The star problem was hard. Let's do it.
What's this?
Is this one right here?
What the hell?
Number 67 or number 2, whatever. A star is estimated to have 2 times 10 to the 36 kilograms, assuming it is a sphere of average radius 7 times 10 to the 5th kilometers. Calculate the average density per cubic centimeter, in grams per cubic centimeter. Oh, man. All right, whatever.
Where's the star?
What? I don't know.
He said in density. Oh, on this one.
All right, let's do it. So, let's write down what we know. We know density.
Equals to kind.
Density is mass over volume equals fraction m over v. Now, my mass is what? The mass is All right. You got to go pretty soon. That's fine. But, in fact, class is finished. You guys can go if you want. However, I'm going to finish off and help people out here. The mass is 2 times 10 to the 36 kilograms. All right. 2 times 10 caret 36 kg. And I think this one was 7. Was it 7? 7 times 10 to the 5th kilometers. All right. 7 times 10 caret 5 km. Okay. All right, so watch down here, and this will kind of help you out. Can you guys see that? Is that too small for you? Is it too small online? Can you see it? All right, cool. So I need to convert this to grams per centimeter, whatever, right? So this is equal to, or no, not equal to, I need to convert. So I want to convert the kilograms to grams. I'm going to probably use a big fraction. And what should I have on the bottom? I should probably have kilograms on the bottom, grams on top. How many grams are in a kilogram? 1,000. I'm just going to put it 1 times 10 to the 3.
You're welcome.
Is that cool?
It's more than cool. Diggity dog.
All right, 1 times 10 to the 3 grams. And I want to convert the kilometers into centimeters. Okay. I'm going to have another fraction. And since there's kilometers down there, I'm going to want a kilometers on top. And do you guys know how to convert straight from kilometers to centimeters?
Mm-hmm.
No, I don't either. Do you know how to convert kilometers to meters?
Yeah.
How many meters in a kilometer?
1,000.
1,000. Cool. I'm gonna write that as 1 times 10 to the 10.
Oh, you
Or
were saying meters. I was still in kilograms.
Are we cool with that?
My brain was worried. Yeah, we cool. I do easy.
All right. That should. Oh wait, I see.
Take again.
Okay. And then what I'll do is I'll convert the meters, which is down here, to centimeters. So I'll make another fraction, and I'll go 1 meter to 100 centimeters. I'm going to write that as 1 times 10 squared centimeters. Are we cool with that?
We cool.
Okay. The reason why now I bet you guys are wondering, like, why the heck is he writing everything down as scientific notation? Why didn't he just put 1,000 up here and 1,000 down here and 100 over here? And the reason being is because I'm going to take advantage of this thing. Now, this I didn't teach you how to do. However, this is where you folks can see this and be like, wow, that's really cool. I'd like to learn how to do that. This is where you can take advantage of not having to use your calculator, at least for the exponents. Because all we're doing is we're counting zeros. Okay, why is the kilometer on top if it's bigger? Bradley's asking, why is that kilometer? Are you asking why the kilometer is on top over here? Is that what you're saying, Bradley? The reason being is because the kilometers was on the bottom over here, and I want to convert it to centimeters, so I need to have that kilometers on top to cancel out the kilometers on the bottom that's over here. Any more questions? Yeah, you don't just always write it so the bigger one's on the bottom. What you want to do is you want to systematically go about it to kill these, like you want to get rid of this kilometers. So you put it, and it's on the bottom over here, so you put it on the top over here to convert it. All right. The reason why I like doing it with scientific notation is because all it does is it becomes down to addition and subtraction. That's it.
Mr. Dalday, I think you screwed something up.
What did I screw up? Oh, you're talking about a homework problem? You're not talking about the problem that's relevant that we're doing right now? Do your homework on your own time, dude.
What is the problem we're doing right now?
Oh, I screwed it up?
What'd you get?
I don't know. I haven't calculated it out yet.
Oh, I got 33.
All right. Anyway, the reason why
The 33 power.
the reason why I like doing this problem, or like doing it with the scientific notation, is because it becomes addition and subtraction. All you got to do is take all the exponents on the tens and add them up if they're on top and subtract them if they're on the bottom.
Oh,
So 36 plus 3, what is it? 39. Minus 5, 34. Minus 3,
31.
31. Minus 2,
29.
29. So my answer is going to be whatever 2 over 7 is times 10 to the 29th power. Cool?
Yeah, bro.
By the way, use your calculator. What is 2 over 7
I
equal
might
to?
have screwed it up, not you.
What is 2 over 7 equal to?
12857.
What is that? 0.28? All right. So my answer is
Gamma glutamate
0.28.
peptidase.
0.28 times 10 to the 29th power. Are we cool with that?
Do we have a Spanish class right now?
I think so.
Oh shit.
All right. 0.28 times 10 to the 29th power. However,
I'll go to
this
Spanish
technically
words.
isn't scientific notation.
Scientific.
Scientific notation, because you want that decimal place to be, you want the number to start off. You don't ever want a 0 to be your first digit in scientific notation.
Bro.
So really, what I would write this as is as 2.8 times 10
in your
to the
class.
28th power. Does that make sense?
Jabba.
So I would actually argue that the answer should be, for this problem, 28, because all I was looking at for is the number in the exponential notation. And I think I said the answer. Whoa! I said it was 6.
I told you screwed something up. I was saying that.
Oh, you know what? I screwed it up in my calculation. It probably could very well be 6. You know why? Here's what I screwed up in my calculation. I said that the volume was 7 times 10 to the 5th kilometers.
What?
How is a volume a length?
Mr. Dolly, you were tired when you did this.
All right, I apologize. What I need to do...
3 points.
No, it's not 3 points. I just haven't finished doing the problem. I'm sorry, okay? All right. What you need to do is you need to plug it through this machine.
But didn't I call it that you screwed something up?
Yeah, you did.
3 points.
So the volume is found by plugging into 4/3 pi r cubed. You plug that into there, and then you do the same exact process that I did. Got it? You just use a different number for this number. You just have to multiply it by 4/3 pi and cube it. Got it? I apologize for screwing that up. But then again, you guys just saw the answer that I wrote down. Because I looked at the answer. I was like, oh, the answer's this. Well, it's also archived.
I never saw nothing.
Anyway, class is finished. See you guys later.
I have an A in your class
Yeah, that's amazing.
in chemistry.
It's crazy.
Well,
All right, I'll talk to you later. Okay, bye. Yeah. Try not to sound too surprised, Mr. Dalday.
It's amazing.
I think the answer is 6. That was what I saw. If you guys wanted to know what the answer is. That's an adorable photo.
Is that your son?
Yeah, that's my son.
Okay.
What I'm wondering is, where's the rest of his body?
Oh god.
Under the sheets.
I know.
Oh, you guys were trying to make a heart.
Doesn't look like a heart?
You didn't get that?
No.
You're
I
horrible.
just got
You're a
that.
horrible person.
I just got it. I thought you guys were just holding it, but then now I see it.
Now you don't.
Maybe I should have them more curved on my fingers. He has such tiny feet. Look at that. Babies are adorable. I'm a big fan of babies. Oh, I didn't stop the recording.